Hi everyone, thank you for joining us for Get Proactive with Pipeline Risk, how to avoid reactive repairs and improve efficiency with Geospatial AI. Your team today will be myself, Rezatec's Marketing Executive, and your speakers today will be Camilla Braithwaite, Rezatec's Product Manager, and also David Johnson, who is one of our Business Development Managers here at Rezatec. So I'll now pass over to you, Camilla.
So thank you so much for joining. I just want to run through what this session is going to cover for you. It's going to discuss geospatial AI. We'll get to that in a little bit, but it's going to talk about how we can identify the top 20% of your pipeline network at risk of failure. We'll also cover how you can proactively manage upgrades and direct resources to the right place. And we'll also talk about reducing leaks with proactive pipeline risk management, and also how to access and utilize new insights with powerful historic and regularly updated new data, and discuss the outcomes of the topics, and we'll discuss the outcomes of the topics for our customers as well. So there is a pipeline break every 2 minutes. And an estimated 6 billion gallons of treated water lost each day in the US alone. That's according to the Infrastructure Report Card 2021 Drinking Water White Paper. That's enough to fill over 9,000 swimming pools. Even more daunting is the fact that the rate of mains breaks has increased by 27% in the last 6 years, according to Utah State University study from 2018. So in addition to frustrated customers, mains breaks also bring negative press, and that stresses the utility and further frustrates your customers. And many communities cannot afford the cost of water loss, but nor can they afford massive pipe replacement programs. They can, however, invest in technologies that reduce loss, improve efficiency, and keep customers informed. So we're talking to lots of different customers globally. And when we listen to their problems that they're facing, we can hear many different difficulties. And there are 3 main themes that we picked up on. And it's interesting, I think you touched on these in the poll results as well. So number 1 for us that we picked up was aging infrastructure. So when aging pipes begin to corrode and weaken, they become more susceptible to breaks. And when you're at the mercy of failures, you spend scarce resources chasing those leaks and then conducting costly repairs. So although the age and material of a pipe is a big factor when it comes to failure, the soil type, the surrounding terrain can also have an influence on breakage. You might get uplift or subsidence. You also might get vegetation, roots and growth. They can all impact the buried infrastructure. So on top of this, you have a growing demand. And also seasonal factors, so increasing extreme weather placing pressure on those pipes. See, the seasonal sort of cyclical action of the seasons also have different stresses depending on whether it's really hot or whether it's really cold. And the challenge for you is that the impact of all these factors is only visible underground. So how can you tell as a network manager or an engineer where these changes or failures are taking place? How can you move from being sort of reactive, chasing repairs, to a much more proactive, cost-effective upgrades program? So number 2 is efficiency. So being reactive gets really expensive. So according to the Water Research Foundation, large diameter pipe breaks result on average in a cost to utilities of more than $1 million each. But there are challenges you face when it comes to implementing proactive upgrade programs. So securing funding for improvement initiatives and gaining public support is notoriously difficult. And one major reason is these systems are much less visible compared to roads and bridges, which makes it much harder to generate public support you need. A really good example of making the point was Burton City's DPW superintendent brought a section of pipe that had recently ruptured to all the public hearings, and he put it on display for everyone to see. And during the meetings, the residents could see firsthand how much their water system had deteriorated. And that really got them to rally behind the project that they were trying to get funding for. But also funding for drinking water infrastructure in general has not kept pace with the growing need to rehabilitate this aging infrastructure. In 2019, the annual water infrastructure capital investment gap was $81 billion US. Furthermore, the ASCE's 2020 water infrastructure study found that the annual drinking water and wastewater investment gap will grow to $434 billion US by 2029. And also COVID-19, Bluefield Research has forecast that the impact of COVID has created a $69 billion US gap that will extend well into the latter part of this decade. So considering the substantially higher cost of remediation or a failed pipe compared to a sort of proactive maintenance approach, following the leaks is a really expensive approach, which many utilities still adopt. So they must now find new innovations to dramatically reduce their expenditure on those reactive repairs and move towards technology that can create efficiencies. Which brings us on to the third theme, which is knowledge and data. So between 2016 and 2026, there's an estimated 10.6% of water sector workers will retire or transfer each year, with some utilities expecting as much as half of their staff to retire in the next 5 to 10 years. To date, the maintenance and upgrade of many pipelines has been based on that experience of the workforce. So local knowledge has been king. And while some utilities already know and factor in the age of the pipeline when they're planning an upgrade or maintenance, very rarely do they have the skills or the technology to combine all the different data sets I've mentioned above, so soils, terrain, pipe material, diameter, length. There are just too many variables to do this manually. And many utilities actually have the data sets they need to start making much more informed, proactive decisions, but it's still challenging to combine those data sets correctly to provide the insights that they need to become more data-driven. They need technology to help predict where the failure will occur ahead of time. That can really help here.
And the fact is that every utility is different. So locally, globally, we see significant variations. In Europe, for example, the pipelines are considerably older than those in the US, and they're often struggling with heavy water losses. Utilities in Europe are heavily regulated to help reduce water loss and manage supply to these expanding populations. Italy, as an individual country, has water systems that are plagued with significant losses. It's estimated that there's more than 40% of all the drinking water in the country's national distribution network is lost to leakage. So quite a significant proportion. Regulation to reduce water loss and to provide secure water as a supply is fundamentally part of their regulation. And as such, many of the water utilities are stepping up the game to comply with these regulations. HERA, for example, had already started exploring risk-based solutions to keep their leakage well below the regulatory levels. But they also wanted to get advantage of a proactive side, so increasing productivity of their teams and improving the break detection rates. Acquedotto del Fiora also invested heavily in improving their data over the last few years, and they've been building on this data to better understand their networks. In the US, we're working with an engineering consultancy, TRC, and this is to service one of their large Midwest utility clients, who is partnered with local communities to save electricity by reducing water loss on their municipal water systems. So fundamentally, and something that we all know, investment in water infrastructure can address so many of these challenges that the water utilities already face. But the question, I suppose, is how do we leverage what we already know or what we already have to help us invest efficiently?
So there is a solution. You're glad to hear. And it helps pipeline managers and leaders to have a light and rather than working in the dark or chasing leaks after they occur. So the 2021 infrastructure report card advises using technologies available and specifically mentions machine learning as a solution to help improve resilience. So rather than continually chasing leaks, there's now this technology that can help you proactively understand network risk to help improve asset maintenance and repair and upgrades. So I'll talk about that now. So what are the benefits to water utilities of using something that's predictive or AI based? So the first one is improving the understanding of the buried assets and making sense of the data a utility has already. Also being able to prioritize where they deploy engineers intelligently, so making sure you focus the money you're spending on upgrade and maintenance on the sections of pipe that are most likely to fail, thereby reducing leaks. Also then, obviously optimizing expenditure and making sure customers are getting the best service. So if you're able to reduce failure where there are more customers affected and high associated costs, you'll optimize both. So there may be several technologies that you need in your toolkit, but what I'm here to talk about is geospatial AI and how that can help you provide the most accurate risk assessment tool to sort of reduce pipeline failure and make the most of the investment in other technologies that you might have as well, so like sensors and things. So we see ourselves as part of a toolkit. First of all, what is geospatial AI? You might, I don't want to make the assumption that you know what it is. So it can be split down into several parts. So first of all, the geospatial data. So that combines location information, attribute information, so things like characteristics of an object, event, or phenomena, and also temporal information, so the time or lifespan at which the location and attributes exist. So then geospatial technology is what enables us to acquire, manage, visualize that geospatial data, and then process it for analysis, modeling, simulations, things like that. And there are different types of geospatial technology out there. Your internet mapping technologies and GPS systems are things that we use now every day. I think it's only my mum that still uses a paper map. Really crazy. You've also got things like GIS, which is a suite of software tools for mapping and analyzing the data. It's probably reserved more for specialists and those who have the time to invest in learning that it's a more complex software program. And then the fourth one is remote sensing. So that's imagery and data collected from space or an airborne camera or sensor platforms. And that's our difference really is we incorporate remote sensing into the geospatial data. So geospatial artificial intelligence is this emerging science, and it utilizes advances in high performance computing to apply technologies in AI, so particularly machine learning and data mining, to extract meaningful information and business insights from geospatial big data. So this is where the difference lies between geospatial technology and technology that delivers geospatial AI. So two examples that we have of our geospatial AI, we have a pipeline risk solution and also ground motion monitoring for dams. So our water pipeline product that combines many data sets to establish a likelihood of failure metric. And this includes multiple years of historic satellite data that we source to monitor ground motion and vegetation growth. We also add a model for the consequence of failure, which includes direct costs of repairing a failed pipe, but also the indirect costs from things like affected businesses, critical infrastructure. And then there's this risk model that then combines these two, the likelihood and the consequence of failure. Second example, which I won't go into so much detail today, is our dam monitoring product. And that accesses 3 years of historic satellite data for each dam. And our method allows us to then extract measurement for the movement of that dam in millimeters, as well as the vegetation vigor and moisture as well. And when we compare these readings over the course of the 3 years to identify what trends and seasonality occur, and that's the sort of what's normal for the dam. And against that, we create this statistical threshold to identify what is an anomaly for that dam. So as with any AI solution, the more data we can wrangle, the greater the quality of that data, the more accurate the model. So this is really going into more depth about how our pipeline risk model works. We include several years worth of environmental data such as soils, topography, and weather. The satellite-based insights include ground motion movement in millimeters and vegetation growth. And then we also include the network data from the utility. So things like pipeline locations and the pipe attributes, so the diameter, the age, and the length, they're the kind of minimum. But if you did have it available, we could also incorporate material, pressure, depth, the slope. And also if you use things like district metered areas, we can also do the analysis for those as well. We could also incorporate spatial data for things like valve locations and meters as well. So really it's about getting as much data as possible into this. And then we build the model using historic incidents. So as a minimum, we need 3 years worth of incident locations. And a bonus for us would be like the incident type, so the leak, the collapse, and also the date, you know, when it was reported, when it was repaired, and the leakage rate. So the model uses machine learning to create a kind of likelihood of failure rating. And we do that for short sections of the network, so not more than 100 meter sections, to make it really accurate. So this chart you're looking at here summarizes the importance each of the data points has in our model training for a network in the US. So the width of each line indicates the influence of each on the accuracy of the model. So if we remove the feature at the top, we would substantially decrease the accuracy of the model. And across all our products, we need the best quality data to train the models we use to give our clients the best accuracy that we can. So the likelihood of failure rating is relative to the network analysed and shown in our platform on a map as a colour-coded section. And it can also include high-risk sections and areas as well. Second part of the product uses the network data to assess the cost of response, repair and restoration of a break. And also the impact, including the proximity to vulnerable buildings, service disruption to customers, collateral damage, transport disruption, and things like that. While we can calculate the criticality using pipeline diameter, the volume of water loss, and the proximity to vulnerable buildings, it's actually further local data that's required to build out the full consequence of failure model with the dollar figure against it. And then by combining the likelihood of failure and the consequence of failure for each section of the pipe, we can then establish a pipeline risk value. And this risk metric is also visualized across the entire network in our platform. So let me show the platform. So when you open the dashboard, there's a clear, easy to use way to access the data analysis we provide. So you can see there are 3 main components: a table of data at the top with data for each section. You've got charts that provide a graphic summary of the whole pipeline network. And then you've got a map view that highlights some of the analysis geospatially. The pipeline's broken down into sections of 100 meters or 328 feet or less to make it easy to locate on the ground. And each pipe section has the raw data for that pipe, but also the analytics that we provide. The pipeline risk value is a risk metric that combines likelihood of failure and consequence of failure. The dollar value actually comes from a cost estimate placed on the consequence of failure model. And you can filter the table based on any of the attributes from the original data or the analytics. So this filter is applied to the whole dashboard. So as I select only pipes with a high likelihood of failure, just here, then it will change the whole dashboard, as you can see. So the map is showing the pipeline risk value, which is our risk metric. The pipeline risk value, or the PRV, can be a dollar value. But if we haven't got estimated local costs for repair, etc., we can use a relative metric created using criteria that are more easily available. So use pipe diameter, estimated volume of water loss, proximity to vulnerable buildings, and things like that. And you can zoom in and see which bits of the pipe network you want to look at. So the chart summarizes the network either by pipeline risk value across here or by likelihood of failure. So you can assess these at a high level. The likelihood of failure is always relative to the network. It actually has a range of values, but the 1 to 5 score we provide here helps prioritize the network. So you can identify the highest 20% of likelihood of failure. And we can also go into the full map. So this main map displays the data analysis in layers, so you can help locate them on the ground. In this demo, we have a layer that shows all the mains for this clean water network. It's based in Canada. And you can also see we have 4 years worth of historic incidents, which we can display as well. The pipeline analysis, it was summarized in the table just now, is viewable here. So as I mentioned, we can build cost into our consequence of failure model. If the utility can provide local costs of replacing the pipe, as well as indirect costs associated with that failure, such as things like liability, transport interruptions and service loss and things, we can factor that all in. We also have the likelihood of failure model. So turn that on, which you can see for each pipe section. So if we zoom in, you can then click on the pipe and that brings up the summary for that particular pipe. And also the other thing that we do is we've created a DMA. This site has one over on the west, so that you can have a look at what a district metered area would look like. And as you can see, we've prioritized that into zones. We've also used the risk metrics to zone the whole network to help the plan works around areas with the highest risk. And then we've got a criticality metric. So this metric highlights the 1, 5 or 10% of the pipeline with the highest pipeline risk value. So that top 1% would include the highest likelihood of failure and the greatest cost or consequence if that pipe were to fail. And then going back over to the left-hand bar, you can see we also provide the satellite-derived data for ground motion and vegetation separated out if you wanted that available. So how does this make a difference to our customers? So one way is to control leakage by prioritizing upgrades to the highest risk of failure sections on the network. So headquartered in Bologna, this Italian multi-utility, Hera, manages more than 35,000 kilometers of water distribution network. They aim to be one of the best Italian multi-utility for its customers, workers and shareholders by supporting a really innovative approach. So they had a collaboration with Bologna University to understand what factors influence the risk of breakage. And Hera was then looking for a technology that had a similar approach, could then help reduce their non-revenue water. So armed with this better understanding of what they needed from the Bologna study, they chose Rezatec's pipeline risk solution for a trial over a relatively small section, which was 490 kilometers. Rezatec initially used 2 years of historic data to predict the 3rd year's worth of breakage, which gave them quite good results. But as with any AI, as I mentioned before, the greater the volume of data, the better the predictive outcome. So adding a 3rd year on improved the model to what we expected, what our expected objective was, which was to find 70% of the breakages in 30% of the network. And that led to a decision to award a further contract for another 2,800 kilometers of the Rimini network and also 400 kilometers in the province next door. So Rezatec's pipeline risk tool allows Hera to identify twice as many leaks compared to the previous methods they were using. That helps them focus investment where it's most needed and helps improve productivity. We're also helping TRC save energy as well as water. TRC is a digitally empowered, environmentally focused global professional services team. And they joined forces with this large Midwest utility to help support water utilities in Illinois. And in Chicago alone, over 60 million gallons of treated water is lost a day, so totaling 22 billion gallons a year from leaking pipes. So this Midwest utility wanted to save electricity by partnering with the local communities and supporting upgrades to their water infrastructure. And TRC proposed a pilot of a solution, and we're just concluding this pilot now with 4 municipal water systems. The initial assessment we did used 2017 to 2019 historic incidents to help train that initial model. And this helped identify 60% of the failures in 30% of the network. The model was then extended to include 2020 incidents, and this then improved the outcome. And that identified 70% of the failures in that 30% highest risk pipe sections in the network. So we're in the process of planning the rollout to the next cohort of potentially about 100 or so municipal utilities off the back of this successful pilot, which is great news. Sorry, I forgot to click to show you the quotes. My apologies. So that was a really successful pilot that's just in the rollout now. So to sum up, you don't have to work in the dark, and you can stop chasing leaks because Geospatial AI will help you identify the highest risk sections of your network to prioritize monitoring, upgrades and repairs. It'll also help you switch to much more insight-driven, effective and proactive upgrades. And that will save you time and money by prioritizing operational activity. So you can use Geospatial AI to supercharge your digital transformation.